Okay, today we're going to be talking about finding out for what x values or where a function is positive and where it's negative. Many times during this semester you'll be asked this question with the function representing several different things. With what's assumed in terms of the prerequisites right now for the course, we'd be asking, for example, find the domain of the function f of x is the square root of x squared plus 2x minus 15 over x squared minus 3x minus 28. Because we have a square root here, we want whatever's inside this square root to be a positive number, or 0. Therefore, the question boils down to saying here is find where this expression, x squared plus 2x minus 15 over x squared minus 3x minus 28 is greater than or equal to 0. And that would find us our domain. Another way to interpret this problem here would be just look at the inside function again here, and it would be asking here is where is that function itself without the square root above or below the x-axis. When it's above the x-axis, the y values are positive. When it's below the x-axis, the y values are negative. So to begin this endeavor, we ask, well, when can the sign of a function change? And when is it going to be staying the same, guaranteed here? There are three typical ways that this can happen. One way that can happen here, and probably the most typical way, is to go from positive to negative, in other words, change the sign, or to go from negative to positive, you need to go through 0. 0 is somewhat of the gatekeeper to cross from one realm to the other. And so if we were looking at a graph of a function, this is just a generic function here, and we want to tell, say at x equal to 3 and at x equal to 8 here, it was 0, the function was 0 here, we can see that these are the values where to the left of 3, the function is positive. To the right of 3, and between 3 and 8 there, the function is negative in this area here. And then to the right of 8 here, the function is positive here. We don't see anywhere else where the change of the sign occurs except where it crosses the x-axis here. And so where the function is equal to 0 is one of the places where a cataclysmic change can take place here. Notice here it doesn't necessarily have to happen that this occurs. We could have a situation, say, where it kind of bounces back up at 3, and then maybe later on here changes the sign, say, at 8 or whatever there. So it does not necessarily have to change sign when it's equal to 0, but certainly where it's equal to 0 is a candidate for where it might change sign. The second typical place where a sign change can take place for a function is when the function is undefined. In particular, we usually will be talking about where we have vertical asymptotes. So for example, where we are dividing by 0, we get an infinite situation. If you want more on that from an arithmetic point of view, see the division involving 0 lecture. This also could occur when you're taking natural log of 0, for example, or when, say, you're taking the tangent of a vertical angle, such as pi over 2 or 3 pi over 2. You could have this happen. Typically, we're going to be seeing it when it's dividing by 0, but you also have many, many other cases here. So what happens here is, say, it approaches negative infinity, as it approaches, say this is 3 here again, as it approaches 3 here from the left, and then it approaches or tends to positive infinity as it approaches 3 from the right. And as we see here, to the left of 3 then, the function is all negative, and to the right of 3 here, the function is all positive. So there's a possibility of it changing sign when the function is undefined. Now, once again, this might not happen, that the sign would change across the vertical asymptote. You could have certainly this situation where it approaches, say, positive infinity from both sides here. And there the sign does not change, but we can't discount the possibility until we find out exactly what happens around there. We can't discount the possibility that the sign might change around a vertical asymptote. Third case, one that we're probably not going to see so much here, but it merits mention, will be where the function is discontinuous. Technically on number 2 we had what we call a discontinuity where we had a vertical asymptote. Of course we could have other discontinuities here, such as say right here where it's positive, say coming up to 3 again, and then to the right of 3 it's negative here, so somehow we had, say, a jump discontinuity here. Obviously, again, does not necessarily have to happen where we have a discontinuity. It could have done something like this and stayed positive around 3 on both sides. But once again, we should consider those cases as well. Again, we're probably not going to be dealing with that so much then in this semester, but you never know. Now, how does this help us to know where the function changes sign? How is that going to help us answer our question here, say, of when a function is positive? Well, the one thing to notice about all of the cases that we just discussed here is that when the function is not 0, when it's not undefined or otherwise discontinuous, the function is the same sign. So let's look at, again, that typical case here. Here's 3 and here's 8 again, very much out of scale. But what you'll notice here is that, well, at 3 the function is equal to 0 here, where it has an x-intercept, and at 8 it's certainly 0, where it has an x-intercept. You notice that's the only places where the function changes sign, which means everywhere else, say, when we look at the intervals here, for all the numbers before 3 here, there's no way it's going to change sign. It could be doing all sorts of crazy things here, but if it's only 0 or discontinuous at 3 and 8, there's no way that it can cross, say, the gatekeeper here to change sign again here. So it's going to play all around here in the positive realm here all the way before 3, but it will never change sign. Ditto here between 3 and 8. It's always going to be negative. It will never change sign for any value. All the values between 3 and 8 for the function are going to give us a negative number. And likewise, all the values after 8 for x greater or equal to 8 will give us a positive value here. So we're going to take advantage of that here in terms of solving our problem. In other words here, all we would need to do here is find, say, if we're talking about before 3 here, pick a value before 3, say 1 or negative 1,000,000 if you want to, and plug that into the function. And whatever value you get for that function, all you need to do is look at the sign and say, hey, that's going to be my sign for all time for x less than or equal to 3. And then do the same thing, pick a point for all the other intervals just to check what that sign must be. And then you're going to be able to tell for which of those intervals is the function positive and for which of those intervals is the function negative. So let's look at our example again that we started with here. So we're looking at, we want to find out x squared plus 2x minus 15 over x squared, let's say minus 3x minus 28. We want to find out when is that positive and when it's 0 here. And also certainly when it's, the main point of the problem of course was finding when this was under a square root, and equivalently we wanted to find the domain of that function. So we want to know for what x values can we plug in that this would become a positive or a 0 number. So let's look at where the function can change sign. And we see the first two cases happen in this problem here. First, when is the function equal to 0? Well, in this case, we have a fraction. Equal to 0. We set that equal to 0. And when is a fraction undefined is when its numerator is 0. Or when is a fraction 0 here is when the numerator is equal to 0. So we check that out and be a little bit careful here. We'll come up with a stranger case a little bit later that this won't happen. In fact, well, I'll deal with that a little bit later here in the lecture. So let's just find out here where this numerator is equal to 0. Lo and behold, during an earlier award ceremony, we rigged this up so that it was nice and factorable, although you have other techniques there to find out how to solve that equation. So we find out that that's factored into x minus 3 times x plus 5. And so, of course, here we get x equal to 3 and x equal to negative 5 are candidates for where the function might change sign. In fact, those are the x-intercepts of our function. The second case here is when is this undefined? For example, with the vertical asymptote. And that's going to happen when our denominator here, x squared minus 3x minus 28, is equal to 0. And we can see we get a number that's not 0 over 0 here. That means it's going to be an infinity situation going on of some sort or another. So we find out when is x squared minus 3x minus 28 equal to 0. And once again, a nice factorable quadratic occurs. We get x minus 7 times x plus 4 equal to 0, which yields x equal to 7 and x equal to negative 4. So we get two more values. Now this rational function here is not going to be discontinuous anywhere else other than where it has those vertical asymptotes. And so we need not concern ourselves with the third case, at least in this situation here. So let's go on. And what this means here is that our intervals, we've now determined our intervals here. We have as critical values here, x equal to negative 5, negative 4, 3, and 7 as possible places where the function might change sign. At negative 4 and at 7 here, I often will write a little u above those places where it becomes undefined, just to remember that we don't want to plug in those values as part of the domain of the function, just for little reminders here. Otherwise, here, within these intervals, negative infinity to negative 5, and then negative 5 to the next one, negative 4, negative 4 to the next one, 3, 3 to 7, and finally 7 to infinity here. Within each of those intervals, the function is guaranteed to remain the same sign. If not, we would have found another place of a critical value, so to speak. Technically, critical value will be used for a very special situation like this a little bit later on in the semester. So we'll call it that for now, but that will have a very special meaning a little bit later on, around chapter 4. So, to figure out here what the sign is within any of the intervals here, our strategy then is to select a value somewhere within the interval and plug it into the function and find out what is the sign. Is it positive or will we get a negative number? So for example, we're not going to do all of these here, but for example, let's look at the interval 3 to 7. And so we want to select some number between 3 and 7, plug it into the function, and find out our sign here. So we had f of x, if you recall, just to rewrite our function here, was x squared plus 2x minus 15 over x squared minus 3x minus 28. And let's pick a nice number here. I mean, we could pick 5.783493 or something like that. But that's not going to be very nice to plug into this function here. It would take some time to punch into the calculator and so on here. But there are certainly nice hunky-dory whole numbers in this interval here, such as 6. So let's plug in 6 into the function here. And by the way, there are many ways to evaluate a function on your calculator. Enter it in like you were going to graph it, say into y1. And there are a couple ways there to generate the values of the function without having to do the arithmetic. You might want to check those out. In this case, when we plug in f of 6 into our calculator, we get negative 3.3 for our y value. Now we don't really care about this 3.3 part here. That's not important here. But what we do care about is that it's negative. And what that tells us here is that every number, every x value between 3 and 7, if we plugged it into f of x, guaranteed we will get some negative number. And so that function is going to be negative throughout that interval for the y values here. And then we can do this very same thing, select a value and plug it in, and for each one of these intervals and see what happens. And when we do that here, and we can make a little chart, I call it a sign chart here for f, and I will list out left to right from smallest to greatest our critical values. Doesn't have to be to scale or anything. Put a little u above those places where the function's undefined. And if we plug in a value before negative 5, we'll find we get a positive number. We plug in a value between negative 5 and negative 4, probably negative 4.5 would probably be the ideal choice there. It turns out we get a negative number. We plug in a number between negative 4 and 3. It turns out we end up with a positive number. We already did between 3 and 7 here, and we found out we get a negative number. And any number that is greater than 7 here will yield positive number, it turns out. Be very careful here. Just because you see this example here where it changes sign at every one of those places here, doesn't, again, as we mentioned before, doesn't necessarily mean it's always going to change sign across the interval. So you do need to check every single interval. Well, now we have found out where the function is positive. And so for our original problem there, where we wanted to know the domain of f of x, of the square root of f of x here, the domain then would be, to solve the original problem here, any x value from negative infinity to negative 5, and we can include negative 5 there because we want to have f of x greater than or equal to 0, and so it was equal to 0 at negative 5. We also can then have between negative 4 and 3, we don't want to include negative 4 because it's undefined there. We do want to include 3 because that's just where the function's 0. And then finally, we also had a third interval where it's positive. We get from 7 all the way out to infinity, or forevermore. Any value greater than or equal to 7 would be just fine. Values that would not be so good for this function would be values between 3 and 7, as we saw before. We would not be able to take the square root of negative 3.3, or say the square root of negative 4.5 would also be bad news for this function. So that's the general strategy there, is to make a sign chart. There's a couple of things to consider. I have 3 major points to make here to think about and consider, maybe to either make life easier or some warnings here. And one would be that if we could write the function as a product or a quotient, we could take advantage of all sorts of rules that we learned long, long ago, maybe 6th grade, 7th grade, pre-algebra and somewhere. That, for example, a negative times a positive gives you a negative number, or a negative divided by a negative mysteriously gives you a positive number. I encourage you on the side here to find out why those make sense to talk about. Why would it make sense for negative times positive to be a negative? But that's another story for another day. For our purposes, though, is if we could rewrite the function as a bunch of products and quotients here. So for example, we had a negative number times a positive number over a negative number here. This will turn out to be, well, negative times positive turns out to be negative, and we already had a negative number downstairs, so this whole thing will turn out to be a positive number. So we can take advantage of that here if we can write our function as a bunch of products and quotients, and only products and quotients. In our particular example, we were able to do that. We didn't do it in the particular example, but we did it somewhat along the way there. We had x squared plus 2x minus 15 over x squared minus 3x minus 28. Well, we could rewrite that. If you remember, these were nice factorable quadratics here, into x plus 5 times x minus 3 over x plus 4 times x minus 7. And what we can do here is take advantage that we've now broken the problem down into 4 different pieces, all involving products and all involving quotients. And what we can say here, for example, is we could only concentrate, say, on x plus 4 and say, hey, the only place that can change sign is when x is equal to negative 4. The sign of whatever x plus 4 is here won't be affected when we're dealing with negative 5 or 3 or 7 or places far away from negative 4. So if you wish, you could actually set up a more elaborate sign chart here, again, with your so-called critical values. Negative 5, negative 4, 3, and 7 here, and a little u's there. And we could split this up into being x plus 5, x minus 3, x plus 4, x minus 7 here, and just look at the individual parts and study those. Well, x plus 5 can only change sign at negative 5. We plug in a value before negative 5, say negative 6, we get a negative value. We plug in a value after negative 5, say 73, and we get a positive value. We know that this is not going to change sign after negative 5. Ditto with x minus 3. We check around 3 here. Plug in a value before 3. Turns out we get negative numbers. And again, it doesn't always work this way. If this was 3 minus x, we'd be leading off with positive numbers here. And then after 3, for example, plug in 6 or 7 or whatever, and you're going to get a positive value. Likewise with x plus 4, will be negative before negative 4, positive afterwards, and x minus 7 turns out to be negative before 7 and positive after. So when we put this all together and we look at our f of x, we see here that for every number before negative 5, we'd be taking a negative times a negative, divided by a negative times a negative. So we'd have a negative for x less than or equal to negative 5. We'd have a negative times a negative over a negative times a negative, which turns out to be a positive over a positive, which turns out to be positive, which was the very same result we found before. Likewise, between negative 5 and negative 4, we'd always have a positive number times a negative, giving us a negative, divided by a negative times a negative, which is a positive, so we'd have a negative times divided by a positive here, and again that gives us a negative value. You can kind of begin to see here that when you have an odd number of negatives, it's going to be negative. When you have an even number of negatives, it's going to be positive. And likewise here, you can figure out the sign by just multiplying and dividing the signs here throughout. And we get the same result that we got before. And again here, be very careful. It doesn't necessarily go negative to positive all the time. If you have 3 minus x, for example, around 3, before 3 here, we plug in, say, 0, we get a positive value. After 3, say, plug in 4 there, we get a negative value. The second consideration here is that, I believe I mentioned before here, is that the sign doesn't necessarily change at every critical value here. The critical values just give you candidates for where it might change sign. Classic example would be this case. Again, a rational function here. They're always the nicest to work with in these problems. So let's say we had this situation. Here, in our f of x, we have here that we see that x equal to 6 will give us 0 both at the top, which will make the function 0, and on the bottom there, which makes our function have a vertical asymptote, essentially an infinite situation there. So we have both situations in the same problem. And in fact, if you plugged in a number here, so for example, if you plugged in f of 2, plugged in 2 into f there, you would get 2 minus 6, which is negative 4, and whatever you get on the other one here, 5. And on the bottom here, you get negative 4, and then on the bottom down here, you get 2 plus 9, which is 11 here. As you can see here, we get a common factor of negative 4, which cancels out. And notice the sign there, negative, it didn't really matter. If these both were positive, it didn't really matter here. All that mattered here is what was left, which was the 5/11ths. So in one case here where you have a common factor on the top and bottom, in this case x minus 6, you can essentially cancel that out, at least from a sign perspective, and just deal with the function x plus 3 over x plus 9. So be very, very careful here that you don't have a common factor muddying the waters here for finding your sign chart. You could go ahead and make a sign chart, say with the x minus 6 in there. That's not a problem. It's just you would be wasting a lot of time in dealing with where it's negative and where it's positive here. In every case there, it will cancel out and not affect the situation there. Another situation where that can happen, or where this can happen here, but let's say we had g of x here, and let's make it a pretty fancy rational function. No common factors going on here, but we do have one factor downstairs in the denominator here, which is a perfect square. And so if you set up the sign chart here, just for the x minus 3 part here, you'll see, and we would put a u because the function is actually undefined there. We plug in any value for x minus 3 squared, and what happens is we plug in a value before 3, plug in 1 for example, we get negative 2 quantity squared, which is a positive number. And we plug in a value after 3, say 8, we get 8 minus 3 quantity squared, again is a positive number. So although 3 was a candidate for the function to change sign, the function didn't change sign at all at x equal to 3. Still need to consider it though, just in case, and still might want to write that down. Another thing to be very careful about would be, a third case here is be careful of constants. So sometimes you might have a common factor here of negative 4 and all sorts of goodies here. X minus 3, x minus 7, x plus 2, x minus 8, and say that's called your f of x. And we want to find out where it's positive and negative here. Well, notice no matter what happens, this negative 4 is certainly going to contribute to the problem here. So you want to include it as one of the factors. Although it never becomes 0, it never becomes 0. And so what do we have here? Negative 3, negative 2, with a u there, 7, and 8, and 8 with a U. You can do all these sign charts here. This would be negative, positive, 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 negative, 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 positive, positive, negative, negative, positive, 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 negative, 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 positive. And you can look at all the signs here all you want here. For example, this would make it a negative here between negative 3 and negative 2. But if you don't talk about negative 4, you're going to be all reverse from actually the correct answer because negative 4 is always negative no matter what value you're at. And so you can see that's going to have a big impact on our sign. So instead of before where we had 4 negatives here, now we put in this extra negative here, the whole thing becomes negative. This one would make it positive, negative, positive, and negative here. So we'd have to be very, very careful here when you have a constant value, a constant factor there being a negative value. If that was a positive 4, would not really have an impact at all because you'd always have positives, and that's not going to change the question of what the sign of the function might be. Finally, the last comment I need to make is, what if you're asked, for example, to find out where this quadratic, and I'll even have it nice and factored out for you here, but it's asking you where is it bigger than or equal to 2 instead of, say, bigger or equal to 0 or less than or equal to 0 or something like that. Well, there are a lot of things, actually an infinite number of 2 numbers here that can multiply out to be 2. But none of those are going to help you because you can't really check all those different infinite number of cases there and check all around them to see when you're bigger than 2 and when you're less than or equal to 2, you have a life to lead. So how can we save some time in doing this here? In fact, a great deal of time is we always try to rewrite these things as a comparing with 0 rather than comparing with 2, just like you did when solving equalities there rather than inequalities. So we could rewrite this here as x minus 3 times x plus 7 minus 2 is greater than or equal to 0. We're looking at the exact same problem. All we did was subtract 2 from both sides. In this case, it's not as nice and factored out, and so we would need to multiply this out. And we wind up with, well, not the prettiest quadratic to deal with, but you can certainly find the critical values and so on. They'll be irrational in this case here, where it might change sign here. But now the big story here, though, is that you're comparing with 0 and can take advantage of making a sign chart.